This is chapter 5. We have a pen here. So this one entitled Thermodynamic Processes and Cycles. This chapter has 4 points. We started with the first one, classification of thermodynamic cycles. We said we can classify thermodynamic cycles based on the purpose, based on the phase change of the working fluid, based on the recirculation of the working fluid. We have Carnot cycle, which is the ideal power generating cycle or power producing cycle, which is all the equations for the Carnot cycle that comes from chapter 4, even the efficiency calculation, everything from chapter 4. Today we will start talking about the real heat engines. And again, remember that in this chapter we need to analyze actual equipment, and also we need to analyze a whole thermodynamic cycles. We focus on the equipment, and by analyzing single equipments, then we can analyze the whole cycle to find the efficiency of these cycles. So again, today we will start talking about the real heat engines, and the first real heat engine we have is Rankine cycle. And again, this one is an example of power cycle because the objective of this cycle is to produce power. We need to get power from this one. If we start with the Carnot cycle, or the components that we have explained in previous lecture for the Carnot cycle, we have pump, we have boiler, we have turbine, we have condenser. These 4 components, we have working fluid moving through these 4 components, and its final state will be the same as its initial state, so it means we have a cyclic process here. So the working fluid, let's assume if we will take this as our initial condition, so it will go to the pump, so it will increase its pressure, then it will go to a boiler, increase the temperature, then it will go to the turbine, decrease the pressure, and then condenser, decrease the temperature to return to the initial condition. These are the main components we have for Carnot cycle, and if you remember when we plot the TS diagram for Carnot cycle, TS diagram because we have temperature on y-axis, entropy on the x-axis, so we have this TS diagram plot representing the Carnot cycle. If anyone remember, we said we have some limitations for using Carnot cycle. Anyone remember what are these limitations? Why we can't have Carnot cycle in real life? Exactly, because of these 2 points. Point number 1, point number 4 are mixtures of liquid and vapor. And it's very difficult to have a pump which is in this path that handle 2 liquids. Also, it's difficult to have a turbine that have 2 phases inside this one. So if we have this problem, what do you think? How can we avoid this limitation? What can we do to points 1 and 4 in order to have like a practical cycle? Do you think we should keep 1 and 4 in the mixture of 2 phases region? Then we need to like move point number 4 more toward the saturated liquid line. Also point number 1 to the saturated liquid line. Point number 4 close to the saturated vapor, so try to keep it close to this line. Even if you will have 2 phases, we need like 1 phase, like have a major phase, dominant phase, and the other is just minor, not affect the performance of the process. So if we can have a TS diagram with this shape, like point number 1, we shift it to the saturated liquid line. Point number 4, we shift it close to the saturated vapor. So if you remember, this point is 100% saturated vapor. So here point number 4 is very close to this point. We can have 96% vapor and just minor is liquid. So this can not affect the equipment performance as much as like here, for example, because here we have significant mixture of liquid and vapor close to like 30%. If we can have TS diagram like this shape, then we can avoid the limitations we have with Carnot cycle, and we can have a real heat engine. And this is the whole idea, or this diagram we have here. This is the one for Rankine cycle. So this, everything that Rankine think of, we have problems with points 1 and 4. Okay, how to avoid these problems? The problem is we have 2 phase, so move these 2 points to the 1 phase region, and we can avoid this one. So and this is what he said. If we have any impracticality associated with Carnot cycle, so we can have eliminate them by superheating the steam in the boiler. So we have here, this is the boiler. the step of the boiler, 2, 3. The inlet to the boiler is number 2. Outlet of the boiler is number 3. So instead of having the outlet of the boiler as saturated vapor, we need to superheat it. So here we have point number 3 is saturated vapor. But here in Rankine cycle, we have this one, superheated vapor. So this was the first thing that Rankine did, superheat the steam outlet from the boiler. Because this one help you when you have the turbine or make the expansion in the turbine, then the outlet of the turbine will be very close to the saturated vapor region. Okay. The other thing he did, condense it completely in the condenser. Okay. The other thing he did, if we have a condenser similar to this condenser here, this step represents the condenser, so we have complete condensation happening. The outlet of the condenser will be 100% liquid. So this is why point 1 here is 100% saturated liquid. Okay. So this is very simply what Rankine did. Just a boiler, superheat the outlet. We don't need point number 3 to be saturated vapor. We need point number 3 to be superheated vapor. Because if it's superheated vapor, goes to the turbine, then the expansion in the turbine will give you point number 4, which is very close to the 100% saturated vapor. So we have one phase dominating the 2 phases we have at least. And for the condenser here, we have full condensation happening, complete condensation happening, and the outlet point number 1 is 100% saturated liquid. If you can do these 2 modifications, then you can avoid the limitations of Carnot cycle, and then we have what is called Rankine cycle, which is the, not considered the ideal, but this is the best real cycle that we can have. Okay? In general, in any power plant, you can have this, a whole plant. We have cooling towers, we have the slacks, we have everything. And then in the middle, you can have some components and Rankine cycle embedded in the heart of this, any power plant. If you have a bigger picture of this one, we can have different type of power plants. You can have coal-fueled power plants. We can have natural gas power plants, oil gas plants, even nuclear, biomass, geothermal, solar power plants, hydroelectric, wind. So even the renewable energy sources, we can have solar fuel cells. So we can have different types of power plants we can have, and you can see in cooled fuel plants, we can have Rankine. The nuclear fuel, even they can use Rankine. They have the oil-fueled Rankine, biomass, geothermal, solar energy system. So Rankine cycle, this one with this simple modification, it generates a real cycle. This real cycle is used in most of the power plants that existing right now. Just very simple modification we have, very simple 4 components we can add, and these 4 components can help us to generate electricity in many plants. Regardless, you are generating electricity from coal, from natural gas, from nuclear, from biomass, from geothermal, even from solar. Regardless of the source you have, Rankine cycle can function effectively in these power plants. Clear? Okay. Any questions so far? Okay. So now let's go and describe what is happening in each step of the Rankine cycle. So again, Rankine cycle, it has the same components of Carnot cycle. We have pump, we have boiler, we have turbine, we have condenser. We didn't change the components, but only we change the performance or the function of each one of them. Okay, and the TS diagram for the Carnot cycle we have. So Rankine cycle, this is the ideal cycle for vapor power plants. Anyone remember why this one is called vapor power plants, not gas power plants? You remember classification of cycles? We can classify the cycles based on the phase into gas cycles and vapor cycles, right? So in gas cycles, do we have phase change? No. In vapor cycles, we have phase change, and this is similar to have here. Here we have liquid, here we have liquid, here at point number 3, superheated vapor. Here we have mixture of liquid and vapor or almost vapor, so we have phase change happening. So Rankine power cycle is considered a vapor power cycle. Okay. This one, it doesn't involve any internal reversibilities, so this is why it's still ideal, and it consists of 4 steps. Step 1, 2, which is happening inside the pump, we have isentropic compression. Okay, we have compression happening, increasing the pressure happening at constant entropy. Isentropic means we have constant entropy. The second step, step 2, 3. This is the step number 2. This is step number 3. 2, 3, this is happening in the boiler. So we have constant pressure or isobaric heat addition in the boiler. Okay, so we don't have isothermal compression similar to what we had in Carnot cycle. Here we have isobaric compression. Third step, we have isentropic expansion in a turbine. This is similar to what we have in Rankine Carnot cycle. And the last step, 4.1, we have constant pressure isobaric heat rejection. Just if you remember the change, Carnot cycle we have 4 steps, 2 isothermal, 2 isentropic. Rankine cycle we also have 4 steps, 2 isentropic and 2 isobaric, not isothermal. Just consider these like changes that we have here. Okay, so the changes we have here in this step. So in Carnot cycle we have the compression isothermal. Rankine cycle we have isentropic. In Carnot cycle we have isothermal heat rejection, but here we have isobaric heat rejection instead of isothermal heat rejection. This one is isentropic in both of them. Here we have isobaric heat addition. In Carnot cycle we have isothermal heat addition. So that the heat addition step, heat rejection step were isothermal, just we make them isobaric. This is the change that we have done in this one. So far clear? Any questions? Okay. How can we analyze the Carnot cycle? How can we calculate the efficiency of Rankine cycle? I keep repeating saying Carnot, but Rankine cycle. So again, this is Rankine cycle. We have the condenser, we have the pump, we have the boiler, we have the turbine. Regardless of the shape, we have the same components, and this is the TS diagram for this one. Just remember we have step 3, 4. This is isentropic. So entropy at point number 3 equal entropy at point number 4. Also 1 2 is isentropic. So entropy at point number 1 equal entropy at point number 2. Point 2 and point number 3, they have the same pressure, not the same temperature. Point number 1, point number 4, they have the same pressure. And since this line is horizontal, so they have the same temperature. But originally they have the same pressure. So in order to find the efficiency of Rankine cycle, then you need to analyze each of the components you have. So you need to analyze the pump, we need to analyze the turbine, we need to analyze the condenser and the boiler, each one of them separately. And this is what we will do in the examples. We will see each one of these equipment. This is what we need to analyze. The key thing in the problems is which one you will start with. And this is based on the given information. So sometimes the information given makes it easy to start with the condenser and then continue the other equipment. Or start with the pump, then continue the other equipment. So this is based on the given information we have. But once you know which equipment you will start with, the same steps will be applied. Okay. If we will start with analyzing the pump, step 1, 2, then this is the equation we can have. The work we have inside the pump has rotating equipment, so we have shaft work. If we record chapter 1, when we explain the work, we have shaft work, flow work, work of expansion, contraction. We explained or we listed the equation that we can use to calculate each one of them. And this is the equation that we will use to calculate the shaft work, which is specific volume times the pressure difference between the outlet and the inlet of the pump. Okay. Here in this equation, and this is equivalent to the enthalpy of the outlet of the pump minus enthalpy of the inlet of the pump. So for the pump, shaft work we have inside the pump, the amount of work inlet to the pump is enthalpy of the outlet minus enthalpy of the inlet equal specific volume times delta P between the outlet and the inlet. Here in this example, we assume that the specific volume is constant. We assume that specific volume at point 1, inlet to the pump, specific volume at point 2, outlet of the pump, these 2 points. The specific volume at each one of them will be the same. And this makes sense because 1, 2, we have liquids, right? 1 is liquid, 2 is liquid, liquid are incompressible, so we don't have significant changes in the ones. So if you can calculate specific volume based on the given information at point 1, or the given information at point 2, any one of them, this will be the specific volume that you will use in analyzing the shaft work. This one is clear? Okay. Then, second step, this one, the boiler, the steam generating, step 2, 3. So Qn, the amount of heat added in this boiler, simply the enthalpy of the outlet minus enthalpy of the inlet. The second step or third step, the turbine, step 3, 4. The outlet work from the turbine is enthalpy of the outlet or inlet of the turbine minus enthalpy of the outlet. And the last one, step 4, 1. Here for the condenser, the amount of heat rejected is enthalpy of the inlet minus enthalpy of the outlet. One thing just to consider, when you calculate Qin or Q out or work of the pump or work of the turbine, here I have one change I did in the formulas. So here for the pump, I said outlet minus inlet. Here for the boiler, I said outlet minus inlet. For the turbine, here I said inlet minus outlet. Here I said inlet minus outlet. You can put it outlet minus in and keep the 4 equations consistent, but you will have like some values will be positive, other values will be negative. This is the only thing. And in the equations, we need to use the positive ones. Okay? So whatever you have, you can know that in the boiler, in the pump, we are using the equations outlet minus inlet, turbine, condenser, inlet minus outlet. This way, this approach will give you all the values are positive, and you can use these values directly in the equations. Or if this will be confusing, keep everything outlet minus inlet, but make sure that any negative value we have, we don't use it, we use the positive value in the equation. This one clear? Okay. So the whole idea of analyzing each of these equipments right now is we need to find enthalpy. We need to find enthalpy at point number 1, enthalpy at point number 2, enthalpy at 3, enthalpy at 4. One of the things we have, you have see part of this in the lead session of the previous chapter, that if you analyze a point similar to point number 4 here, which is mixture of liquid and vapor, we have term called the quality, which is this one. So here in this one, if you need to analyze the turbine or if you need to analyze the condenser, both of them has H4, enthalpy at point number 4. And enthalpy at point number 4 is mixture of liquid and vapor. So how can we calculate the enthalpy of this one? The enthalpy for this one cannot be calculated from the steam tables, because we have a steam table for saturated liquid or saturated vapor, subcooled liquid, superheated vapor, but not in or not if we have mixture of liquid and vapor together. So this is why we have H4 is calculated from this equation that have a new term called the quality. And quality, this is the fraction of the vapor we have in the mixture. How can we calculate quality? Quality is specific entropy at point number 4, which is entropy at point number 3, right? So if you have S3, this will be S4 automatically, because this process is isentropic. Minus specific entropy of saturated liquid divided by specific entropy of saturated vapor minus specific entropy of saturated liquid. Even here we have HL. This is enthalpy of saturated liquid, enthalpy of saturated vapor, enthalpy of saturated liquid. So what are these values? What is HL, HV, SL, SV? So here, HL and SL, this is specific enthalpy, specific entropy for saturated liquid, 100% saturated liquid at the condenser pressure and temperature. So point number 4, if this point number 4 is 100% saturated liquids, it will be here. So the values here at this point, this is SL and this is HL. Likely here in Rankine cycle, this point the same as point number 1. So the enthalpy you calculate at point number 1, this will be this HL. The entropy that you can find at point number 1, this will be this SL. The other thing, point number 4, if it exactly lies on the 100% saturated vapor, so this will be HV and this will be SV. So in order to find enthalpy or entropy at point number 4, just At the same pressure, go to the 100% saturated liquid, find enthalpy, entropy. At the same pressure, go to 100% saturated vapor, find entropy, enthalpy, and then use these two values to calculate the quality, the percentage of vapor you have, and then use it in this equation to find the enthalpy at point number 4. After we finish all of this analysis, then we need to find thermal efficiency, and thermal efficiency, the equation that we have, the net work obtained divided by the inlet amount of heat in the boiler. 1 minus Q out over Q in. What is net work? It's Q in minus Q out, or work in minus work out. Work in, this is the work pump in, which we analyzed here when we have the pump. Work out, this is the turbine we have. Or in terms of enthalpies, we can put everything in this one. We can say efficiency of Rankine cycle. This is the work we have for the pump, minus work we have in the turbine, divided by the enthalpy change we have around the boiler, which is Qn. So this one represent work net, and this one represent Qn in the boiler. So any one of them, just you can make the same calculations and do it. Is it clear?